I'm Earl Campbell, Head of Architecture at Riverlane. So I'm going to talk about decoding fault-tolerant quantum computers. So if you don't know Riverlane, Riverlane's a quantum computing startup that's moving towards building an operating system for quantum computers. And what that really means at the moment is focusing on 3 core modules. One module thinking about the algorithms that we want to execute and building out the infrastructure for that, the software for control systems, and then software and FPGAs and ASICs for solving the decoding problem. So that's what I'm going to focus on today. And I break the talk up into 3 parts. First, I'm going to motivate why we need fast real-time decoding. So we heard a little bit about this the morning, that actually for our quantum computer, we can expect that there's going to be a large HPC infrastructure required to go with it. And the heaviest of all the heavy loads carried in that HP infrastructure is actually going to be carried by the decoding part. However, most people kind of think that you need fast decoding for the wrong reasons. And so the second part of the talk, I'm going to give a kind of researchy presentation about a recent paper we had on a method that we call parallel window decoding. So the important thing about this work is that it teaches us to kind of rethink what our metrics should be and what our targets are and requirements for building fast decoders. So in the last part, I'm going to talk about our upcoming product that we're going to publish a paper about, Deltaflow.Decode. So this is our FPGA decoder, and I'll show you some preliminary results on how it's performing. OK, so if you're not familiar, this is a cartoon picture of the surface code. And what I've illustrated here are 2 measurement outcomes that have given a result that shows something has gone wrong nearby. And the problem in error correction is to try and find the most likely error, i.e. the actual error that happened, that explains this set of measurement outcomes. So in this particular instance, one possible solution is a pair of X errors on these qubits, and we consider ourselves successful if we get the correct answer up to some equivalences. But that was a really, really toy picture, because in that picture, I assumed that every single measurement result that you got was accurate, when in practice, measurement errors can happen, do happen, and are often the biggest source of error in your system. So if we want to think about what the decoding problem looks like, if we include the possibility of measurement errors, we end up with a kind of graph problem that we have to solve, like this one that I've illustrated here. So here, every single horizontal edge is a possible qubit error that could happen, and every single vertical edge is a possible measurement error that could happen. So at the end points of these edges, so if you've got an orange edge, that means that error actually happened. And the endpoints, the highlighted vertices, are the flags that the user, the controller of the quantum computer observes. So what you're essentially given is a graph, a set of vertices, and you've got to find out a set of paths that connect these vertices up using the smallest possible weight possible. And this is a really, really hard computational problem. So not highlighted on this graph are possible errors such as circuit level errors and other things which we call hypergraph errors, but everything that I say in this talk will carry over to that setting. OK, so on this slide, I'm going to explain a concept called Pauli frame updates. So the point here is that on the previous slide, we had this whole history of data. And after we decoded it, we learned that at some point in the past, an error happened. So we can't reach back into the past and perform that correction. So what can we do? Well, it turns out that most error correction schemes use only a limited set of operations called Clifford gates. And you only need to know one important thing about Clifford gates, and it's this circuit identity here, which says that if I have some error E that happens in the past, and it's followed by some set of Clifford gates executing an error correction circuit, then this is equivalent and can be efficiently classically computed to another Pauli error, E prime, at some later point in time. OK, so we can always just not perform the correction and update what we think the correction should be. There's a little bit more to it, which is that if at any point in time I perform a measurement, a Pauli measurement, then when I pull this error through the circuit, it might change the outcome of that measurement. So what this teaches us is that error correction isn't actually about physically correcting errors and doing physical corrections. What error correction is about telling us what our measurement outcomes actually are. So we can't trust our measurement outcomes until we've decoded all of the syndrome history, all of the data that we've pulled out of our quantum computer up to that point in time. OK, so if you don't need to physically perform error correction, why do we need fast decoders? Well, the key thing is that Clifford circuits aren't universal. They're efficiently classically simulatable. And so at some point, you have to go beyond using Clifford circuits. And it's as soon as you start implementing non-Clifford circuits that you encounter a possible problem, which Barbara Terhal named in this review paper that she wrote, which we now call the backlog problem. So I'm going to present how I think about the backlog problem. And so in this slide here, every single line represents a logical qubit. So it encodes it embodies many physical qubits. And what we're trying to do is trying to implement one non-Clifford gate, a logical T gate. And the textbook way of doing this in most fault-tolerant architectures is to use magic state teleportation. So we've got some state, the T state, our state psi, which we want to perform the T gate on. We do a C0 gate, and then we perform a measurement. And then after we perform this measurement, we've got to apply a correction depending on the outcome of that measurement. But if this is an error-corrected circuit, then actually there's going to be some delay after we perform the measurements, because we need some amount of time to do our decoding. And that's why I've drawn this kind of delay line going off to the right with some amount of time, which I've labeled ft minus t. So this here is what we're going to call the backlog. There's always some amount of data that I have a backlog of that I haven't even started trying to decode yet. And the amount of that backlog is essentially telling us what the time lag is between performing our measurements and the next time we can do a logical operation. So how long does this have to be? Well, I've kind of put a lower bound here, which is f times t. So I'm just assuming a very mild assumption that's true for almost every decoder you've ever come across, which is that the amount of time it takes to run the decoder scales linearly with the amount of data that it has to process. So that scaling constant here is just given by f. And then I'm subtracting the amount of time that has elapsed up to that point. OK, so that's fine. Actually, we can handle some latency. It's not a problem. Whilst we've got this latency happening, we're still doing error correction. We're still collecting new data from our system. So let's look at a second non-Clifford gate. So now we again do introduce a magic state, perform a C0 gate, make a measurement, and introduce some backlog to account for the amount of time we have to spend decoding. But now I've got to take all the amount of time that has elapsed up till this point, multiply it by f. And so I'm going to get a term that looks like f squared. So if f is a constant that's bigger than 1, this backlog could be bigger than the first backlog. And if I do this n times, I'm going to end up with a situation where I've got a backlog that scales like f to the n. So if f is a constant that's bigger than 1, that means that you now have an exponential runtime algorithm. So you've taken something and added an exponential overhead onto it. That's something that's completely unacceptable to us, and so this is a non-starter for building a universal fault-tolerant quantum computer. OK, so there was something implicit in everything that I said there, which is that we already know how we're going to do decoding on the fly. I was talking about, look, I've got this time progression from left to right, and I'm just going to take the data in this chunk, and I'm going to decode that chunk and then move onwards. And so really what we're doing there is we've got a more general notion of decoding. We've got something that I would call an inner decoder and an outer decoder. So the inner decoder is something that you might have heard of before, like a minimum weight perfect matching decoder or a union find decoder. It's essentially some module that takes in a very well-defined problem and then solves it. And then the outer decoder is some meta algorithm that's essentially responsible for assigning tasks to one or more inner decoders and then reconciling the output from them. And so what I'm going to be talking about in this part of the presentation is this new idea of outer decoding, which we're calling parallel window decoding. So before I tell you what that is, I'll just mention the kind of prior art, which everyone has thought of in the past, which is called sliding window. So the sliding window approach takes your syndrome history. So here, remember, the vertices represent flags that have detected that something has gone wrong nearby, and they've got to be paired up. So here I'm just using one axis for time and one spatial axis, and I'm ignoring the extra spatial axis you would have for the surface code, just to keep the picture clean. But for all of the numerics, it is really for the surface code. OK, so we can't decode over the whole history in one go. So what we do is we pick out a window. Our outer decoder chooses a window of data and passes it to the inner decoder, which could be matching or union find or something else. So in this instance, I've highlighted some edges in solid green to say these are the tentative edges that the inner decoder has suggested we apply corrections for. OK, but can we trust all of those outputs? Certainly, at the top half of the window, we can't. And the reason for that is that for some of these defects, maybe they should match upwards or some of it match to the side, but we don't know the answer because we can't see past the top of the window. But lower down in the window, we are quite confident. So we've got a buffer region that buffers us from the uncertainty zone where we don't know what's going on. So for the part that I've kind of highlighted green, we can commit to all of those corrections there. We're highly confident that those corrections are correct. And then we slide the window up. We run the inner decoder again to find some tentative corrections. We select those, and then we raise up again. So this is a method that was proposed many, many, many years ago. Surprisingly, I'm not aware of anything in the literature that implemented it until we did our implementation. And so these are some numerics from our implementation of this prior art. So the left-hand side looks like one plot, but it's actually two plots. It's two plots superimposed, and you can't see the difference because they're essentially indistinguishable. So what it's showing you is that if you use Slido window decoding with an inner decoder, or you just decode over the whole history of information you get out of your quantum computer, the results are indistinguishable in terms of the logical error rate. So that's a good outcome. On the right-hand side, what we're looking at is the speed of the decoder, the frequency at which it decodes. And what we can see is something that is well known, which is that as we make the code bigger, as we make it suppress more and more errors, what we see is that the speed of the decoder slows down. That's bad, because there was this constant f that appeared in the backlog problem, which was essentially related to 1 over the speed. So what you're seeing here is that there's always going to be a code size that you get up to, where if you use this sliding window method of decoding, at some point you hit the backlog problem and you have an exponential runtime overhead. So what that's telling you is that if you use the kind of textbook way that everyone talks about doing quantum computing, there's actually a finite size algorithm that you can go up to until you hit an exponential runtime overhead. And this is the point in the talk where I pivot to say how we solved it. So this is the paper from the archive with my co-authors all at Riverlane. So we had a simple suggestion. I might note that the Alibaba group actually has a nearly identical proposal which they put on the archive the same day. The proposal was to take this massive backlog of data and to do some parallel processing. But I think one of the key differences in both how we think about it and how Alibaba think about it is that what we're doing in parallelization is to parallelize in the time direction rather than some spatial direction. So we take our history of data with the time axis running up, and we take 2 chunks of it, or 3 chunks, or 4 chunks, or how many we want that are not overlapping, and we pass that data to our inner decoder, and then we set it off running. There is a slight difference, and the slight difference is now that if I think about where I'm highly confident about what to do, it's now the middle of the region. I have to put a buffer above and below to account for the fact that I'm only confident about my corrections if they're kind of well separated from regions where I don't know anything. Okay, so my tentative corrections are returned by my inner decoder. I lock in the ones that are in this green highlighted commit region. And then I choose a new set of windows that I'm going to pass to my inner decoder. But now you can see that I used a kind of denser shade of orange. So what I'm illustrating here is that I'm going to consider this whole region to be inside the commit region. So all of the corrections that are returned by my inner decoder at this stage are going to be accepted. And the reason that we can do this is that both above and below these windows, we're already highly confident about where the errors occurred. And so we don't need a buffer region to separate ourselves from those parts of the space-time diagram. So we find a set of tentative corrections returned by our inner decoder, and then we accept them as Pauli frame updates. And what we see is that we've decoded an arbitrary amount of data, assuming that we've got enough windows running in parallel. So here I've just shown 2 windows in each layer, but there could be hundreds of windows in each layer. And what's the runtime of this algorithm? Well, you can see we've just done 2 layers. So that means that it's 2 times the amount of time it takes to decode an individual window, or the worst time it takes to decode an individual window. So if we return back to this backlog problem and ask how would we execute a series of gates in a quantum computer, then we would still add some latency between when we perform a measurement and when we perform the next logical gate or the next Clifford correction. But now the amount of latency we have is no more than 2 times the amount of time it takes to decode an individual window. Is no more than 2 times the amount of time it takes to decode an individual window. So that means that no matter how long it takes to decode an individual window, the runtime of the algorithm is always going to be linear in the number of gates that you want to execute. So you've eliminated this exponential problem that we saw earlier that Barbara Terhal had highlighted. It doesn't mean that we can stop thinking about building fast decoders, unfortunately. We still need fast decoders, but it changes our understanding about why we need them. It's because what we see here is that there's a factor that contributes to the runtime of the quantum computer, that's equal to the amount of time it takes us to decode each one of these windows. So if there's just one thing that I want you to take away from this talk, is this simple message. It's that the speed of your decoder determines the logical clock rate of your quantum computer. It's not that if you can't decode fast enough, you can't do quantum computing. It's just if you can't decode fast enough, you'll be doing very slow quantum computing. So here are some results similar-ish to the ones I showed you earlier, but this time we're talking about parallel window as the outer decoder that we've chosen. So on the left-hand side, again, there are two plots here, but it's really, really hard to see the difference between them because they look essentially the same up to error bars. And what's happening is that we've got a simulation that's been run with parallel window, and then another simulation that's been run taking the whole syndrome history, which would be impossible to do in real time, and comparing them in terms of the logical fidelity they achieve. And it's essentially indistinguishable up to logical fidelity. What's the plot on the right-hand side? This is showing you what the speed of the decoder is at different code sizes as a function of the number of processors. So I was saying that you could achieve, let's say that you haven't got an infinite number of classical processors to help you solve the decoding problem. You've only got a finite number, n par. Then you would expect maybe that if you have 10 of these processors, you would be able to speed up your decoder or process 10 times as much syndrome data as you would do otherwise by using parallel window decoding. And indeed, that's what we see here. All of these lines are essentially linear, showing that the speed does increase with the number of processors that we use. There's a very slight sublinearity here, because these simulations were done in Python, and Python isn't that good at parallel processing compared to other computing architectures such as FPGAs. And so we expect that if we go to something like an FPGA or an ASIC, this parallelization problem won't really be there so much, and it'll be almost perfectly linear. So I promised that I would give you a teaser of some upcoming results as well as describing the parallel window paper that we've already put out. So the really big thing that we're hoping to share with you all in more detail soon are the results from our Deltaflow.Decode product. So this is an FPGA decoder. It's a design that could also be mapped onto ASIC if needed. We have some preliminary results that are in this talk and also on the website under the technical white paper section. And there should be an archive paper coming out soon with details of how the actual FPGA performs. So here's some preliminary data. It's not the actual FPGA data, it's data from a simulation of the FPGA. I've seen the FPGA data. It is real, it does exist. I'm just not authorized to show it to you quite yet. And so what we're looking at on the left-hand side is, again, the speed of the decoder. The different color bars show different error rates, and what we can see is that the speed of the decoder goes down as we increase the more and more qubits. And there's a dashed line representing when it becomes too slow, and we have to resort to something else. If we didn't have parallel window decoding, then we would just have the backlog problem, or would be in trouble. But what the plot on the right-hand side is showing us is that each one of these different curves now shows how fast we would be decoding if we used more parallel processors to help us with the decoding problem. And we can see that, yes, indeed, if we add enough parallel processors, we can bring everything down to below the dashed line and get to whatever code distance we require. So thank you for listening.
Thank you, Earl. I guess we have time for one question. Is there a question?
I guess it's an unfair comparison, but how much faster is the FPGA as compared to your Python decoder?
It is an unfair comparison because if you actually build something out, say even in an ASIC, then if you do it, the node size that you use is not going to be as fast as the one that you would use to build a MacBook or something. So in fact, the advantage is not necessarily in the speed, the throughput. The reason why you would go to an FPGA is the latency issue. So if you try to use a decoder connected up to a laptop, then what you'll find is that you'll submit some task, it will have to go through the network card, it'll get stuck in a queue, that queue doesn't have a deterministic kind of bounded length, and so there's a big question here about what the right metric should be to use when you compare a software decoder versus a hardware decoder, because the throughput, i.e. the amount of time a software decoder decodes each experiment as part of a batch could be much, much faster, but that's because the request has not come through a network card.